Okay, in our final lesson on vectors, we're going to look at cross products, some of their properties, and cross products in component form. So just real quick, we had the vector A crossed with the vector B, and that gave us the vector C, which was A, B, sine theta, and then from our right-hand rule, n hat, it's a vector answer, and we said that was our vector C, and we said the vector C, because our right-hand rule is based on that karate chop right-hand rule, it is always perpendicular. The vector C is always perpendicular to the plane made by vector A and B when you draw them from a common origin. Well, we have some properties then for some special cases. When the two vectors A and B are orthogonal, they're at 90 degrees, we will get the maximum value for the cross product magnitude because sine is 1. We get a minimum value when A and B are parallel or anti-parallel because we get 0 degrees or 180 degrees. Now, I'm not going to go into detail for examples of what it's used for in physics. I have very quickly up here pre-annotated that torque, which is kind of the rotational oomph you get when you want something to turn, is given by a cross product, R cross F. So if you think of R as the leverage, the lever arm, and F as the force you are using, to get something to rotate about a hinge, like a door, right? The doorknob is put as far away from the hinge as possible, giving us the greatest R. If you really want to push the door open and have it rotate quickly, you use a large force. And ideally, to get the greatest torque or rotational oomph, you will push at 90 degrees, and that's what we do naturally when we open doors. We're going to do more of this when we talk about rotations later in the year, so I don't want to go into great detail about it, but I just wanted to give you an idea that it does have usefulness in physics. We're not doing cross products just because. Okay. Like we were doing for dot products, I do need you all to be cross product machines so you can take the cross product and get the values. We definitely will put more meaning to it as we go along. So what I have down here I don't want to spend a lot of time on because we're going to be working within the plane of the page. So the plane of the page is this over here. X and Y axis will be in the plane of the page. We'll do our right hand rule and we will be getting z-hats, positive z-hat thumb out of the paper and negative z-hat thumb into the paper almost exclusively. Now, we do want to make note that if we have the vector A and B that we are crossing along the same axis or anti-parallel along the same axis, but on the same axis at all, we always get no result, null result for our cross product. If we were going to work in three-dimensional coordinate systems, which again is a little hard on a two-dimensional sheet of paper, we get that positive z coming out of the paper and negative z going into the paper. But now when we do our cross products, if we did want to do a y hat z hat cross product vector, if we had some vector A in the y hat direction, some vector z in the z hat direction. So let's put them right in there. So this is our vector A, this is our vector B. Now if we do A cross B, we will get an n hat pointing in the positive x direction, and for right now I don't want to get all involved in having you have to calculate all of these correctly. As long as you are good within the plane of the page, thumb into the paper, thumb out of the paper, we can work on what happens over here, getting our right hand rule properly together when we're in the classroom and we can take a look at the coordinate system and look at our hands actually moving. Okay, so what I have on this page is a component form cross product for us to look at. Now, just like when we did dot product, the component form cross product can be distributed. So I have an example here where we have a vector A, for example, is given by this vector, a vector B is given by this vector, and we're taking the cross product of the two. And that's what I have shown down here, where we are going to distribute through. So we're going to take x cross x, x cross y, x cross z. And now we don't get as much cancellation. So we do get 0 when they're in the same direction along the x-axis, but we don't get zeros here. So we have to take 3x and cross it with 4y, and 3x and cross it with 3z. Okay? So we would continue distributing through, and that's how we get the numbers here. But I'm, again, not going to pull you through this because there is a way for you to calculate it without having to go through all of those distributions. Now, if you look at what we have here, we will always get an answer where the result of the cross product is perpendicular. So that was the result here that I am showing, that if we use that kind of messy XYZ that I was talking about and did our cross products and actually did 3x cross 4y, 3x cross 4y is a positive z hat answer, so that's this one down here. All right? So 3x cross 4y gives us 3 times 4 times z hat. So we would have to keep going. The x z hat will be in the y, so we have our cross product 3x hat cross 3z hat gives us this one here, because that's a y hat answer. Remember that the cross product result is always 90 degrees to the plane of the vectors that they were generated from. And we could do it this way, and we could keep getting our answers, and we would get the final result when we did all of this would equal this. However, there's a nice mathematical procedure to follow that gives us this answer without having to go through all of that distributing through. We are going to set up a 3 by 3 matrix and take a vector determinant. So the first row, I'm going to blow things up here so we can see it a little better. We're going to take the first row is going to be the unit vectors, x hat, y hat, z hat. The second row is going to be the vector A. So we're taking 3x hat minus 2y hat, 1z hat, but we just put in 3, negative 2, 1. And then we're taking vector B, which is negative 1 x hat, 4y hat, 3z hat, and making that the third row of our 3 by 3 matrix. So you are first going to do your 3 by 3 matrix, and then you are going to add columns at the end of that matrix, x and y, and the first column is going to repeat the first column of the matrix that we just wrote. The y is going to be repeated over here, and then you are going to put in diagonals down and to the right, and they are positives. Diagonals down and to the left are negatives to keep everything lined up. And then we are going to match the x's, the y's, and the z's. So what do I mean by that? So what we are going to do is we are going to take the x's, I will do in blue. So we are going to take negative 2 times 3, which is negative 6, times positive 1, and that gives us a negative 6 x hat. So we are going to get negative 6 from that multiplication. We are then going to go over here and do 1 times 4 times negative 1 and get negative 4, and that is our x hat answer. That is the negative 10 that we have here. We're going to do the same thing for the y. So we're going to take our y and our y. We're going to do 1 times negative 1 is negative 1. we are then going to do 3 times 3 is 9 times negative 1 gives me negative 9. And that's my y hat answer, and that is the answer here. And I'll leave it to you to show that when you do the z, that you get, oh, I left my z off. No, I have my z here. I have my red z going down to here, and I have my blue z going down to here, that when you do that, you will get positive 10. So take a look at this, go back and do it slowly, annotate your notes slowly, see if you can follow what was done here. On the next page is an example, so I would like you to pause the video, attempt the problem on the next page, and then unpause it, and I will go through the solution with you. So pause the video. Okay, hopefully we've unpaused, and we'll go back and look at the solution. So we have the vector A is 3, negative 4, 2, and that's the first vector we put in after we put in our x hat, y hat, z hat. So we make our 3 by 3 by x hat, y hat, z hat. We put in A, then we put in B. Notice we have negative 2x. We don't have any value for y, so we put in 0, and we have 3. We then tag on our additional x column and y column. Please make sure you confirm you are going to do your matrices, your matrix determinant, vector determinant properly, and we can do the first one together to get the minus 12 correct. So we're going to do minus 4 times 3 times positive 1 is minus 12, and in the other z or other x direction, we have x here and x here. We have 2 times 0 is 0, so that's why we get the 12 in for that answer. So we can go over this in class as well, but I think you have the idea. Please be careful not to use your calculator determinant function. This is a vector determinant, so unless you have a fancy calculator, and I realize some of them do allow you to take vector determinants, you cannot just use your calculator with the regular determinant.